Hello students, today we shall see few examples on application of Leibniz theorem, and then we shall see statements of Taylor's theorem, Maclaurin's theorem, and some deductions from these statements, and then we shall see some examples on expansion of function using Taylor's expansion. Okay, so first we see few examples on application of Leibniz theorem. Example number 19, y equal to x square e to the power x. If y equal to x square e to the power x, then show that yn means nth derivative of y is half n into n minus 1 y2 minus n into n minus 2 into y1 plus half n minus 1 into n minus 2 into y. So that is nth derivative expressed in terms of first derivative, second derivative, and y. So y equal to x square e to the power x given. Now let us differentiate this line with respect to x. Here u into b, product rule. So y1 dy by dx means y1 equal to x square into derivative of e to the power x is e to the power x plus e to the power x remains, derivative of x square is twice x. But this x square e to the power x is again y from this line number 1. So it is y plus twice x e to the power x. So this is line number 2. Again let us differentiate this line with respect to x to find y2. So this y1 will become y2 and this y becomes y1, dy by dx is y1 plus here twice x e to the power x. So derivative of e to the power x is e to the power x, it remains twice x into e to the power x plus e to the power x remains. Now derivative of x with respect to x is 1, so it is just 2. So from line number 2, twice x e to the power x value is y minus y1, sorry y1 minus y, y1 minus y we have used from this line number 2. So finally we get y2 equal to twice y1 minus y plus 2 e to the power x, line number 3. Now we want to find nth derivative. So differentiating this line number 1 with respect to x n times and using Leibniz theorem, if we apply Leibniz theorem we get x square into nth derivative of e to the power x, it is e to the power x plus nc1 first derivative of x square twice x, n minus 1th derivative of e to the power x is e to the power x plus nc2 second derivative of x square means derivative of twice x, it is 2, and n minus 2th derivative of e to the power x is e to the power x, and next derivative of this 2 will be 0, so we stop here. Now this x square e to the power x is y and twice x e to the power x value is y1 minus y, already we have used, this is y1 minus y from line number 2, and then nc2 value is n into n minus 1 by 1 into 2, and 2 e to the power x, see value of 2 e to the power x from this line number 3 is y2 minus 2y1 plus y. So y2 minus 2y1 plus y you have used here from number 2 and 3. Now rest is simple simplification. You can check this yn is equal to this, whatever given in the question is got. Then example number 20, if y equal to x square minus 1 to the power n, then prove that x square minus 1 yn plus 2 plus twice x yn plus 1 minus n into n plus 1 yn equal to 0. So y is x square minus 1 to the power n. Differentiate this line with respect to x, we get y1 equal to n into x square minus 1 to the power n minus 1 into derivative of x square minus 1, chain rule twice x. Now let us multiply both sides by x square minus 1 so that it will become again y. So multiplying by x square minus 1 both sides, x square minus 1 into y1 equal to n 2x means 2nx, and x square minus 1 to the power n minus 1 will become now x to the power n, but this is y, so it is twice nx y. Line number 2 we have got using line number 1 value of y. Now here it is yn plus 2, so we again differentiate this line number 2 with respect to x, differentiating line number 2 with respect to x to find y2, actually relation involving y2. So x square minus 1 y2 plus y1 remains, derivative of x square minus 1 is twice x, u into b rule, product rule, right side also twice n into x into y, again u into b rule, so x into y1 plus derivative of x is 1 into y. Then x square minus 1 y2 plus y1 is here, yn is there, so if we side change and take common 2 common, x common, so 1 minus n, 2 into 1 minus n, x y1, we have got minus 2ny, side changed, number 3, this is line number 3. Now this line we differentiate n times with respect to x, and using Leibniz theorem what we get, x square minus 1 y2 u into b rule, but we shall consider this y2 as u and x square minus 1 as b. So x square minus 1 remains, y2 will become yn plus 2, nth derivative of y2 is yn plus 2 plus by Leibniz theorem nc1, then nc1 into what? Increased derivative of first factor, decreased derivative of second factor. So x square minus 1 derivative is twice x, and yn plus 2 now will become yn plus 1. Then plus nc2, increased derivative of this twice x, it will be 2 only, and yn plus 1 will now become yn, decreasing derivative of this. And next derivative of 2 is 0, so only 3 terms in Leibniz theorem. Plus here 2 into 1 minus n x into y1. Again x into y1 is, in this case we again apply Leibniz theorem, of course considering y1 as u and x as b. So x remains, y1 will become yn plus 1, nth derivative of y1, plus nc1, increased derivative of this factor and decreased derivative of this factor. So it is nc1 into 1, because derivative of x is 1, and then yn plus 1 will become yn, and next derivative of 1 is 0, so only 2 terms in Leibniz theorem, minus twice ny, so derivative of nth derivative of y is yn written, because twice n is constant. Now putting the value of nc1 is n, here nc2 is n into n minus 1 by 1 into 2, and then 2 into 1 minus n, I have written here n minus 1, giving here minus sign, and x into yn plus 1, then plus 2 into 1 minus n, nc1 is again n, and yn is there, but there is another minus twice n yn, so this yn taken common, minus twice n, and rest is simplification. These things you can check yourself. Okay, so answer is got, proved. Example number 21. If y equal to sin m sin inverse x, then show that 1 minus x square yn plus 2 minus twice n plus 1 x yn plus 1 plus m square minus n square yn equal to 0. Hence find yn 0, that is value of nth derivative of y when x equal to 0. So y equal to sin m sin inverse x. First we shall find the relation involving y2. So differentiating this line with respect to differentiating this line number 1 with respect to x, what you get? y1. dy by dx means y1. Sin m sin inverse x, derivative of sin is cos. Sin of anything is cos of that thing, into derivative of that thing, inside thing is m sin inverse x. Derivative of m sin inverse x is m into 1 by root over 1 minus x square. Derivative of sin inverse x, 1 by root over 1 minus x square, all of we know. So sin of anything, cos of that thing, into derivative of that thing. Now this 1 minus x square, root over 1 minus x square, cross it. So we have crossed, and then we got this line number 2. Now again differentiate this line with respect to x. y1 into root over 1 minus x square, say u into b rule here. So derivative of y1 is y2, root over 1 minus x square remains, plus the y1 remains. Now root over 1 minus x square derivative is 1 by 2 root over 1 minus x square into minus 2x. Root of u is 1 by 2 root u into du by dx. So 1 by 2 root 1 minus x square into derivative of 1 minus x square minus 2x, directly written. Right side is m cos m sin inverse x, means cos of anything. So cos of anything derivative is minus sin of that thing into derivative of that thing. So again m sin inverse x derivative is m into 1 by root over 1 minus x square. So we cross this root over 1 minus x square. When it comes here, 1 minus root over 1 minus x square, root over 1 minus x square becomes 1 minus x square. Root gone, y2 minus here 2 cancels, and root over 1 minus x square crossed from here. So it will be only minus x y1, and here m square, and this sin m sin inverse x is y, so it is minus m square y. Using line number 1 we have got. So 1 minus x square y2 minus x y1 plus m square y equal to 0, just side changing. So this is our line number 3. Now differentiate this line with respect to x n times, and using Leibniz theorem we shall get 1 minus x square y2. 1 minus x square remains, y nth derivative of y2 is yn plus 2, plus nc1, Leibniz theorem, nc1, increased derivative of 1 minus x square means minus 2x, and decreased derivative of yn plus 2 means it will be yn plus 1, plus nc2, increased derivative of this minus 2x, derivative is minus 2, and decreased derivative of this yn plus 1, it will be yn. Next time derivative of minus 2 is 0, so we stop here. 3 terms in Leibniz theorem. Then x into y1, again here Leibniz theorem, x into yn plus 1, because derivative of nth derivative of y1 is yn plus 1, then plus nc1, and derivative of x is 1, and decreased derivative of yn plus 1, it will be yn, and next derivative of 1 is 0, so we stop. 2 terms in Leibniz theorem, and third term is m square y, m square constant, and nth derivative of y is yn written. And then this is nc1 value is n, nc2 value is n into n minus 1 by 1 into 2 gets cancelled, and x yn plus 1, here nc1 is n, and plus m square yn. So simple simplification here. this two gets cancelled, and twice n plus 1 x yn plus 1, because there is another x yn plus 1 taken this in one place, and then here minus n square plus nyn. This minus nyn and plus nyn will be getting cancelled, and m square minus n square yn. Okay, line number 4 we have got. Short first part. Now we want to find value of yn when x is 0. So when x equal to 0, from 1 2 3 4 we get, means from very beginning when x is 0, if I put here x 0, sin inverse 0 is 0, so y will be 0. When if I put here x 0, sin inverse 0 is 0, but cos 0 is 1, so y1 will be m. Like here, if we put x 0 0, then y2 will be minus m square y, but y we have got 0, so it will be 0. See, when x 0, from 1 2 3 4 we get y is 0, y1 is m, because cos 0 is 1, y2 plus m square y0, but y2 is minus m square here, but y is already we have got 0, that's why y2 is 0. And then putting x equal to 0 in line number 4 we get yn plus 2 plus m square minus n square yn 0. Yn plus 2 plus m square minus n square yn 0 means yn plus 2 equal to n square minus m square. Side changing we get number 5. This is the recurrence relation. Replacing this n by 1 2 3 etc. in number 5 we get. If we put n1 we shall get y3, if we put n2 we shall get y4, like this. So y3 will be 1 square minus m square y1, and value of y1 is m we have got, so it is m into 1 square minus m square. Now if we put n equal to 2 here, y2 will be, y4 will be, n plus 2 will become y4, y4 will be 2 square minus m square, here 2 square minus m square y2, but y2 is 0, so answer is 0. y5 will be 3 square, here if we put 3, y5 is 3 square minus m square y3, but y3 is, we have got m into 1 square minus m square, so y5 value is m into 1 square minus m square, 3 square minus m square. And y6 will be, again if we put m equal to n equal to 4 square minus m square into y4, but y4 is 0. Actually all even suffix terms will be 0 for y. So y7 is 5 square minus m square y5, and putting the value of y5 we get y7 is 1 square minus m square, and 3 square minus m square, 5 square minus m square with an m factor in the beginning. Okay, and so on. So therefore in general what you get, yn 0 means value of nth derivative of y when x equal to 0 is 0 if n is even. All even suffix values are 0, and odd suffix values is m into 1 square minus m square, 3 square minus m square, 5 square minus m square, dot dot dot, n minus 2 square minus m square if n is odd. See, for y7 we stop at 5 square minus m square, for y9 it will stop at 7 square minus m square, so for yn it will stop at n minus 2 square minus m square. Okay, so got. Example number 22. If y equal to sin inverse x whole thing square, show that 1 minus x square yn plus 2 minus 2n plus 1 x yn plus 1 equal to minus n square yn equal to 0, and hence find yn 0. Here yn 0 means value of yn at x equal to 0. Various notations are used. I have written here yn first bracket 0 or first bracket yn suffix 0 means value of yn when x equal to 0. The answer is given here, similar to previous example. Like example 21 you can do. Okay. Example number 22 also. Prove that dn dxn means nth derivative of x to the power n sin x equal to factorial n into p sin x plus q cos x, where p is 1 minus nc2 x square by 2 factorial plus nc4 x to the 4 by 4 factorial minus dot dot dot. Q is nc1 x minus nc3 x cube by 3 factorial plus nc5 x to the 5 by 5 factorial plus dot dot dot. It is not infinite set, it will stop. It will depend on n even or n odd. The last term will depend on n is even or n is odd. Okay, let us see. Let y equal to x to the power n sin x. This is u into b, where u is x to the power n, b is sin x. So nth derivative of x to the power n sin x means d to the power n, y means yn. So Leibnitz theorem if we apply here, un v plus nc1 un minus 1 v1 nc2 un minus 2 v2 plus nc3 un minus 3 v3 plus nc4 un minus 4 v4 plus nc5 un minus 5 v5 plus dot dot dot, last term is ubn. This is Leibnitz theorem. We have written up to b suffix 5 because here nc5 is there in the answer also. So what is un? U is x to the power n. So un means nth derivative of x to the power n is n factorial, standard result. Sin x remains, b remains, plus nc1 un minus 1, n minus 1 at derivative of x to the power n. This is standard derivative number 1 we have done. So x to the power n, n minus 1 at derivative will be factorial n by factorial 1 into x into cos x, because v1, v is sin x, so derivative of sin x is cos x, plus nc2. Then n minus 2th derivative of x to the power n is n factorial by 2 factorial x square, and derivative of cos x is again minus sin x, plus nc3 into x, n minus 3th derivative of x to the power n is n factorial by 3 factorial x cube, and derivative of this minus sin x is minus cos x. Then nc4 n x to the power n minus 4th derivative, so it is n factorial by 4 factorial x to the power 4 sin x, because minus cos x, derivative of this minus cos x is sin x. Actually we decrease derivative of first factor and increase derivative of second factor. nc5 x to the power n minus 5th derivative is factorial n by 5 factorial x to the power 5, and this derivative of sin x is cos x. So we have written like this, and last term is x to the power n remains, means u remains vn, and nth derivative of v is sin x is sin n pi by 2 plus x, all of you know. So this is a finite series. Now we collect the coefficients of sin x and cos x. Just collecting coefficients of sin x and cos x, we have got this factorial n into this expression into sin x plus this expression into cos x, and then it is given in the question, this is p, this is q, so it is factorial n into p sin x plus q cos x. So proved. This is nth derivative of x to the power n sin x. Okay, so these are the problems we have solved using Leibnitz theorem, rather application of Leibnitz theorem. Now we move to Taylor's theorem. This is generalized mean value theorem. We have studied in class 12 mean value theorem, Lagrange's mean value theorem, Rolle's theorem. So this is generalized mean value theorem, that is Taylor's theorem. And of course we shall do it with Lagrange's form of remainder term for a function of one variable. Taylor's theorem with Lagrange's form of remainder for a function of one variable. Let f is a function from the closed interval third bracket a comma a plus h to r. Real valued function. F is a real valued function. Domain is closed interval a comma a plus h, and codomain is r, set of real numbers. So f is a function such that f and all its derivatives up to n minus 1th order are continuous in the closed interval third bracket a comma a plus h. In the closed interval, f and all its derivatives up to n minus 1th order are continuous. And second condition is the nth derivative fnx, nth derivative of this function exists for all x in the open interval first bracket a comma a plus h. That is, for all x belongs to first bracket a comma a plus h. Means what? A greater than x, a less than x, less than a plus h. X is strictly between a and a plus h. Derivative exists, nth derivative. Then there exists a real number theta with this range 0 less than theta less than 1. There exists a real number theta between 0 and 1 such that f of a plus h equal to fa plus h by 1 factorial f dash a plus h square by 2 factorial f double dash a plus h cube by 3 factorial f triple dash a plus dot 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 h to the power n minus 1 by n minus 1 factorial f n minus 1 at derivative at a plus rn. Last time we have written rn. What is rn? Where rn is h to the power n by n factorial f n a plus theta h, means nth derivative of the function f at the point a plus theta h. And this Rn is called Lagrange's form of remainder term, or just simply Lagrange's form of remainder. Lagrange's form of remainder term in Taylor's theorem. So this is Taylor's theorem statement. Function is continuous with its derivatives up to n minus 1th order in the closed interval. Nth derivative exists in the open interval, and then there is a real number theta between 0 and 1 satisfying this condition. Last term is Rn. Rn means h to the power n by n factorial f nth derivative at a plus theta h. This is called Lagrange's form of remainder term in Taylor's theorem. So this is Taylor's theorem, generalized mean value theorem. If n equal to 1, particular case, Taylor's theorem is nothing but Lagrange's mean value theorem we have studied in class 12. That is, in that case, this becomes f of a plus h equal to fa plus h f dash a plus theta h. H f dash a plus theta h. N equal to 1, f dash a plus theta h. H by 1 factor means h. So this is mean value theorem we have studied already. And if n equal to 2, then Taylor's theorem becomes f of a plus h equal to fa plus h by 1 factorial f dash a plus h square by 2 factorial f double dash a plus theta h. Last term will be f double dash, here n is 2, f double dash a plus theta h, h square by 2 factorial. So this is Lagrange's mean value theorem of second order. And note 2, if the function f has continuous derivatives of every order in this closed interval third bracket a plus a comma a plus h, every order, and if Rn tends to 0, remainder term tends to 0 as n tends to infinity, limit of Rn is 0, then f of a plus h becomes fa plus h by 1 factorial f double dash f dash a square by 2 factorial f double dash a cube by 3 factorial f triple dash a plus dot 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 up to infinity, because Rn tends to 0. It is an infinite series now, not stopping. And this is known as Taylor's infinite series. Taylor's infinite series. But condition is limit Rn should be 0. Rn tends to 0. For an infinite series, for convergence of the infinite series, general term should tend to 0 as n tends to infinity. So that condition is used here. So this is infinite series. Now, if a plus h equal to x in this infinite series, a plus h equal to x or h equal to x minus a, then this series becomes what? Fx equal to fa. H is x minus 1, a x minus a by 1 factorial f dash a, h square means x minus a square by 2 factorial f double dash a, h cube means x minus a cube by 3 factorial, here 1 f triple dash a means, okay, f triple dash a, and then plus dot dot dot. Okay, this is Taylor's expansion of fx. This is Taylor's expansion of fx in ascending powers of x minus a in an infinite series in the neighborhood of the point x equal to a, means x should be near to a, otherwise this series may not be convergent. So when x is in the neighborhood of the point x equal to a, then this series is convergent, and then in that case it becomes fx, and that's why this is Taylor's expansion of fx, okay, in the neighborhood of the point x equal to a. Now in particular, if a equal to 0, then what it becomes? Fx equal to f0 plus x by 1 factorial f dash 0 plus x square by 2 factorial f double dash 0 x cube by 3 factorial f triple dash 0 plus dot 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 up to infinity. This is known as Maclaurin's expansion of fx in ascending powers of x in an infinite series, and of course it is in the neighborhood of origin. When x is near to 0, then it will be convergent. So this is Maclaurin's expansion, special case of Taylor's expansion. Separately we shall do again here. It is note 3, if a equal to 0 and h equal to x in Taylor's theorem, a equal to 0, h equal to x in Taylor's theorem, here a equal to 0 and h equal to x in Taylor's theorem, then what you get? Then fx equal to f of 0 plus x by 1 factorial f dash 0 x square by 2 factorial f double dash 0 x cube by 3 factorial f triple dash 0 plus dot 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 x to the power n minus 1 by n minus 1 factorial f n minus 1 at derivative at 0 plus Rn. This is known as Maclaurin's theorem with Lagrange's form of remainder term Rn. What is Rn? X to the power n by n factorial f n at derivative at theta x. A plus theta x it was. A is 0 and theta h was there, but h is x. So this and theta is between 0 and 1. So this is Maclaurin's theorem. Separately we shall state again it. So Maclaurin's theorem, separate statement. Original statement. Let f is a function from closed interval 0, h. Previously we have taken h equal to x. H may not be x. X may not be h. X may be less than h also. So that's why general one is f is a function from the closed interval 0, h to the set of real numbers r, such that this f is a function satisfying the two conditions. What is the condition? What are the conditions? F and all its derivatives up to n minus 1th order are continuous in the closed interval third bracket 0, h. So similar to Taylor's theorem condition. Roman 2, actually Maclaurin's theorem is nothing but Taylor's theorem special case. So number 2 condition is the nth derivative fnx exists for all x in the open interval first bracket 0, h. That is for all x belongs to first bracket 0, h. That is 0 less than x less than h. X is between 0 and h strictly. Then there exists a real number theta with 0 less than theta less than 1, means between 0 and 1, such that fx equal to f of 0 plus x by 1 factorial f dash 0 x square by 2 factorial f double dash 0 x cube by 3 factorial f triple dash 0 plus dot 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 x to the power n minus 1 by n minus 1 factorial f n minus 1 at derivative 0 plus Rn, where Rn means x to the power n by n factorial f n at derivative at theta x, and this is called Lagrange's form of remainder term in Maclaurin's theorem. So this is Maclaurin's theorem statement. Here of course x belongs to first bracket 0, h. Here x belongs to first bracket 0, h when we say that fnx exists, and the expansion is valid for any x, of course, for any x in the interval. Okay, our domain is closed terminal 0 h, so x can be h also, so better we mention here real number theta. Then there exists a real number theta with 0 less than theta less than 1 such that fx equal to this. Better we mention then for any x, for any x belonging to this closed interval, whatever x may be. For any x belongs to this closed interval, there exists a real number theta with this. X, if x changes, theta will be changing. Okay. So this is Maclaurin's theorem, separate statement. Note, if the function f has continuous derivatives of every order n in third bracket 0, h, means in closed interval 0, h, and if Rn tends to 0 as n tends to infinity, that is limit Rn 0 as n tends to infinity, then this Maclaurin's theorem becomes actually fx equal to f0 plus x by 1 factorial f dash 0 x square by 2 factorial f double dash 0 x cube by 3 factorial f double dash 0 plus dot 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 infinity. Already we have seen in Taylor's theorem in the deductions. So this is Maclaurin's expansion of fx. This is known as Maclaurin's expansion of fx in ascending powers of x in an infinite series in the neighborhood of the point x equal to 0. In the neighborhood of the point x equal to 0. So this is Maclaurin's expansion. Problems will be done later. First we shall do examples on Taylor's expansion. Example 1. Number 1. Find the Taylor series expansion of log x by z about the point x equal to 1 and hence evaluate log 1.1 correct to 4 decimal places. So here function is log x by z. Let fx is log x by z, then f of 1 is what? Log 1 by z equal to 0. We want to find expansion in powers of x minus 1. That's why all the derivatives will be at the point 1. So f dash x 1 by x, f dash 1 is 1. F double dash x is minus 1 by x square, f double dash 1 is minus 1. F triple dash x is x, this is x to the power minus 2, so derivative will be minus minus plus 2x to the power minus 3. F triple dash 1 is 2, means we can write 2 factorial. F4 derivative means derivative of this will be minus, will be coming here, so minus 2 into 3 into x to the power minus 4. Minus 3 minus 1 is minus 4. So f4 derivative at 1 is minus 2 into 3 means minus 3 factorial. F5th derivative is this minus 4 will be coming here, so it will be 2 3 4 x to the power minus 5. Minus 4 minus 1 is minus 5. So f5th derivative at 1 is 2 3 4 means 4 factorial and so on. Therefore by Taylor series expansion of function fx about the point x equal to a, we get this is the result we know about the point x equal to a. Expansion is this: f of x equal to f a x minus a by 1 factorial f dash a x minus a square by 2 factorial f double dash etc. Here a equal to 1 in this case. So our expansion is in powers of x minus 1. Fx equal to f1 x minus 1 by 1 factorial f dash 1 x minus 1 square by 2 factorial f double dash 1 x minus 1 cube by 3 factorial f triple dash 1 etc. Now we put the values. Fx means log x, f1 is 0, f dash 1 is 1, f double dash 1 is minus 1, f triple dash 1 is 2 factorial, f4 derivative 1 is minus 3 factorial, f5th derivative 1, next term was f5th derivative 1, that is 4 factorial etc. So if we put these values and simplify, we get x minus 1 square by 2 plus x minus 1 cube by 3. 2 factorial and 3 factorial cancelling we get 3, 4 factorial and 3 factorial cancelling we get 4, 5 factorial and 4 factorial cancelling we get 5. So this is not factorial 5, this is only 5, this is only 5, so this is not there, this is not there. Okay, which is required expansion. Now if we put x equal to 1.1 in this series, so that x minus 1 is 0.1 means h is 0.1, we get from 1 this line, what you get, log 1.1 equal to 0.1, 0.1 square by 2, 0.1 cube by 3, 0.1 to the 4 by 4, 0.1 to the 5 by 5, dot dot dot. Okay, so 0.1 square divided by 2, 0.005, 0.1 cube divided by 3 is this is a recurring, still we have taken up to 5th place. 0.1 to the power 4 by 4 is up to 5th, 6th place we have taken etc. Next will be 5 number of zeros, so we are not writing. because question is correct to 4 places of decimal. So you see that there are 4 zeros. Next there will be coming 5 zeros. So answer is 0.0953, correct to 4 places after decimal. So got the answer. Example 2, expand log cos x by Taylor's expansion about the point x equal to pi by 3. About the point x equal to pi by 3 means all derivatives will be at the point pi by 3 and expansion will be in powers of x minus pi by 3. So fx is log cos x here and f of pi by 3 is log cos pi by 3. Cos pi by 3 is half log of, you can write 2 to the power minus 1 means minus log 2. F dash x is log cos x 1 by cos x into derivative of cos x minus sin x, so it is minus 10x. So f of pi by 3 is minus 10 pi by 3 minus root 3. F double dash x, derivative of 10x is sec square x. So it is f double dash pi by 3 is minus sec square pi by 3. Sec pi by 3 is 2. So it is 2 square. Minus 2 square means minus 4. F triple dash x, sec square x derivative is 2 sec x into sec x 10x. So minus 2 sec square x 10x. Minus is already there. So f triple dash pi by 3 is 2 sec square pi by 3 10 pi by 3. Sec square pi by 3 is 2 square. So it will be 8 and it is root 3. So minus 8 root 3. F triple dash x is that we have simplified this sec square x written as 1 plus 10 square x. So it is ultimately minus 2 10x plus 10 cube x. So it will be easier to differentiate. For derivative x will be 10x sec square x, 10 cube x is 3 10 square x into sec square x, chain rule. So again this sec square x is written as 1 plus 10 square x, 3 10 square x, again 1 plus 10 square x. So finally 1 plus 4 10 square x, 3 10 to the power 4x. It will be easier to find 5/5 derivative, that's why. So f4 derivative at pi by 3 is, here we have substituted 2 sec square pi by 3, 3 10 square pi by 3, sec square pi by 3 here. So it is 2 square root 3 square again 2 square. So finally minus 80. 9 36 and 4 40, so minus 80 and so on. Therefore by Taylor's series expansion of the function fx about the point x equal to a means here pi by 3, we get directly we have written instead of x minus a x minus pi by 3, expansion in powers of x minus pi by 3. We have written the formula, Taylor series expansion formula, and then fx is log cos x and all the values substituted here and got this expansion. So this is required expansion of log cos x in powers of x minus pi by 3 in Taylor series expansion, but x should be near to pi by 3 so that the series is convergent. Example number 3. Prove that sin x is equal to sin a plus x minus a cos a minus x minus a square by 2 factorial sin a minus x minus a cube by 3 factorial cos j for some j between a and x. So here fx is sin x, fa is sin a, f dash x cos x, f dash a is cos a, f double dash x is minus sin x, f double dash a is minus sin a, f triple dash x is minus cos x. And this third derivatives, up to third derivative we have written because here it is only third degree terms, which are all continuous in any interval a comma a plus is third bracket. Sin cos trigonometric functions, these are continuous, sin and cos are continuous everywhere. Therefore by Taylor's theorem with n equal to 3, with n equal to 3 we get a real number theta with 0 less than theta less than 1 such that f of a plus h equal to f a h f dash a plus a square by 2 factorial f double dash a square by 3 factorial f triple dash a plus theta h. This is Taylor's theorem with n equal to 3. F a plus h is sin a plus h, f a is sin a, f dash a is cos a, f double dash is minus sin a, and f triple dash a plus theta h. Triple dash x is minus cos x, so it will be minus cos a plus theta h. Now let a plus h is x and a plus theta h is j. Therefore h is x minus a, and what is j? J lies between a and a plus h, because see theta is between 0 and 1, so a plus theta h surely lies between a and a plus h. Theta is a fraction, theta is a number between 0 and 1, so j lies between a and a plus h, that is j lies between a and x, because we have taken a plus h is x. So we have got final answer, sin x equal to sin a x minus a, h is x minus a, cos a, h square by means x minus a square by 2 factorial sin a, and h cube means x minus a cube by 3 factorial cos a plus theta h is cos j. So proved. Example 4. Expand x to the power 4 minus 3x cube plus 4x square minus 2 in powers of x plus 2 using Taylor's expansion. This is a polynomial. Higher derivatives will be 0. Let us see. So this is fx, and here we have to expand in powers of x plus 2, means x minus a is here x plus 2, because standard expansion is in powers of x minus a. So x minus a is x plus 2 means here a equal to minus 2. So we find all the derivatives at minus 2. First f of a means f of minus 2 is calculated 54. Then f dash x calculated from this line and value substituted minus 2, f dash minus 2 is minus 84. Then sorry, f double dash x again calculated and then minus 2 substituted, value is 92. F triple dash x calculated and then value substituted, minus 66. F fourth derivative is 24. So at minus 2 also it is 24, and because constant fourth derivative, so all higher derivatives from fifth onwards will be 0. Therefore by Taylor's expansion about the point x equal to a means here minus 2, we get fx equal to f of a x minus a by 1 factorial f dash a x minus a square by 2 factorial f double dash a, etc. And then put x minus a, replace x minus a by x plus 2 and a by minus 2. So values substituted, and here fifth derivative onwards all are 0, so we have substituted up to fourth derivative only, because fifth derivative onwards all terms are 0, all derivatives are 0 being a polynomial. So finally putting the values, simplifying, we get 54 minus 84 into x plus 2 plus 46 into x plus 2 square minus 11 into x plus 2 cube plus x plus 2 whole thing to the power 4. Means this is an expansion in powers of x plus 2. This is by Taylor's expansion we have got. Example number 5. Using Taylor's expansion, express the polynomial this in powers of x minus 1. Exactly similar to example number 4. Here a is 1. All derivatives we will calculate at 1. And number 6. Expand sin x in powers of x minus pi by 2 using Taylor's expansion. This is similar to example number 2, where we have used x minus pi by 3. Here it is x minus pi by 2, means all derivatives we will calculate at pi by 2. So thank you for today.